began talking about multidimensional wavelets, and there's very significant, in my opinion, complexity that arises when you go from one dimension to two dimensions. And so from some point of view, it may seem like a technicality. From another point of view, it's a significant body of knowledge. Of course, from the third point of view, it's still just something one uses some of the time. But it's a very interesting component of the whole theory. So last time we talked about the dyadic case, and we showed what sorts of results are true. And the interesting thing which pops out immediately when one looks at tensor products is that in the dyadic case, one does sort of a natural thing. Then if you're given a multi-resolution analysis with one scaling function, then you're forced into three wavelets you need in order to do the theory. So that has a little bit of a shock value, but then you see that it really makes sense when you write out these projective tensor products that three wavelets are required. In fact, if you're in d dimensions and do the dyadic case, then you need 2 to the d minus 1 wavelets in order to get a wavelet off a normal basis. And intuitively, it makes sense. Now, by going to higher dimensions, though, things generalize in another way, and that's what I'm going to talk about tonight. And let's begin. So, a lattice lambda contained in RD is defined as lambdas L of ZD, where L from RD into RD is an invertible linear transformation. Or to use slightly fancier language, it's an automorphism. And there are several equivalent words that are used to define what I'm going to define now. I'm going to call them dilation matrices, but definition of the dilation matrix. So let lambda be a lattice. So in particular, lambda is contained in RD. And lattices are what we think of as lattices. Okay. And let A be a D by D matrix properties that it's inclusive, namely A of lambda is contained in lambda, and so that means A leaves lambda invariant. And B if lambda is an eigenvalue of A, then the absolute value of lambda is bigger than 1. Okay. And so such a matrix is called a dilation matrix. So in this case, A is a dilation matrix. Well, this property here, property B, seems like a strange one at first glance, but property B ensures that we are dilating in all directions. And I'm going to actually do a calculation to show how it really arises. And another thing we're going to show is the following. We'll show, so that's the end of the definition. We'll show in a moment that if A is a dilation matrix, so that means there's a lattice associated with it, then, following some sort of tradition, we'll use the number Q for the value of the matrix, then Q, which is the determinant of A, is actually a positive integer greater than 1. Okay. And so the standard example is one that we talked about last week, namely let lambda be equal to ZD in RD, and let A equal the matrix M I. D by D identity. And M belongs to N take away. So this is all pretty easy so far, but we're going to get a little more complicated pretty soon. So that's a dilation matrix, and the determinant is easy to evaluate. It's M to the D. And of course the case that we talked about last week was when M was equal to 2. But the point is, just the first level of getting fancier than dyadic, let's take M to be any integer bigger than 1. So let's verify this little fact here. So let's verify one. And proof of 1. So okay, so we have a dilation matrix, all its eigenvalues are positive. And so that means that, therefore, the determinant of A, we can write down the determinant of A in terms of its eigenvalues, right? Standard result of determinants is the product of all the eigenvalues. So that's just something from linear algebra. All the eigenvalues are bigger than 1. So in particular, this is bigger than 1. So we have to show then that that number is an integer. Well, lambda, a lattice. Now, this is not going to be a big complication, but this is one of those things that one usually says it is easy to see that this is an integer, but you have to do a little calculation. So lambda lattice implies there exists this invertible mapping, this automorphism in RD, such that L of ZD is equal to lambda. And since A is a dilation matrix, we have A of lambda is contained in lambda, and that implies then, well, it's actually equivalent to that is A of L of ZD is contained in L of ZD. Okay? And so it's not going to prove that, right? So since what? Nothing. I just was checking to see that. So since L is invertible, we can write L inverse A L of ZD contained in ZD. Okay? And so, therefore, this matrix has integer values. So therefore, L inverse A L has integer values. And hence, if I look at the determinant of A, what do I have? This is equal to the determinant of L inverse times the determinant of A times the determinant of L, since this is actually equal to the determinant of L on the inverse, and it's invertible, so it's not certain. But this is then just equal to the determinant of L inverse A L. And we know that these guys has integer values, so this is all contained in and it's a positive thing, it's contained in that. So from the very beginning, we know it's bigger than 0, bigger than 1, so that's all. Now, in one of the some of the technicalities one has to do in this subject is one has to do a lot of change of variables. So let me write down the change of variables formulas that I'm going to need. So the first one, so change of variables formulas. first one I wrote down over here. One, let F be in L1 loc of RD, and let G be in L infinity of RD. Assume that G has compact support. Why not? And let A be an automorphism of RD. Once again, all that means is a linear automorphism. I just mean a linear map from RD into itself. Okay, then, as we used in the previous fact, the determinant of A inverse is equal to the determinant of A inverse is not zero. And if I look at the composition, F composed with A operating on G, that's just equal to, by definition, the integral F of A of X, G of X. When you do the change of variable formula route, that becomes equal to, that's over RD. And that becomes equal to the integral over RD of F of X, G A inverse of X times the determinant D, determinant of A inverse dx. And of course, there are much more complicated formulas, but that's all I need for now. Can you get way over here, Sure. Because so I don't have to erase too much. So the next one I want to write down is we use the adjoint, 2. So let A be an automorphism of RD with adjoint A star. Then A star is an automorphism of RD onto itself, and A star inverse is equal to A inverse star. This is standard linear algebra, and the determinant of A star is equal to the determinant of A. And then the final change of variables, there's no change of variables there, but I need that for the following result. The final change of variables is the following. I wrote down. I engaged in overkill here, but I only really need 3.
So when you say that A is an automorphism, you just mean that it's bijective? It's bijective now?
Yeah, a linear bijection.
Linear bijection.
Yeah. And right. As I said, it's a fancy word. And since autos are in the news these days, so let A be an automorphism of RD. A, if F is in L1 of RD, then the composition is also in L1 of RD. And we have a nice formula. If we have something in L1, we can take its Fourier transform. And the Fourier transform of that composition is 1 over the determinant of A F hat composed with A inverse hat. And basically there's an analogous statement which I'm not going to need tonight, analog for temper distributions. Okay, so that's what I'll be using these changes in. Now, if we have a situation of having an automorphism, so if A is an automorphism of RD, it induces a unitary operator called UA going from L2 of RD into L2 of RD, where a function F goes into the determinant of A, 1/2, F of A. And you remember unitary maps of the property that U operating on its adjoint is equal to the adjoint operating on U is equal to the identity. Okay, so now, just as we defined a multi-resolution analysis for the dyadic case, we can define a multi-resolution analysis in this segment. And it is the following. Definition of an MRA. So, an MRA associated an MRA of L2R D. Now you can imagine doing wavelet theory on groups, which one can, of how this might generalize. I mean, it's all been done, but you can see how it can be done. So, an MRA of L2 of RD associated with a pair A lambda dilation. And lattice. Is a scaling function phi in L2 of IV. One doesn't say this in public, but it's surprising that with all the names they've given these functions, phi and whatever, that they don't say, and they do say scaling function, but why not call the VJs the scaffolding? So, I mean, why not? So, and it's a scaling function phi and scaffolding. Maybe that'll be the last time I have to say VJ, such that the following holds. For all J in Z, VJ properly contains VJ plus 1. So basically, I'm at my usual definition only with A's, where and lattices where I had the twos and the integers before. 2, F belongs to V0 if and only if top K F belongs to V0 for all tall lambda. For all lambda in the lattice. 3, F belongs to Vj if and only if F of A of X excuse me, belongs to Vj plus 1 for all J. That is Vj is equal to UAJ, J composition of V0. And then for the union of the VJ's closure, as J runs through all the integers, is L2 of IV. And 5, the intersection of the VJ's is equal to this 0 function in L2. And then finally, the translates as we run over the lattice of phi is an up and all basis for V0. Okay, so I spent a lot of time writing it down, but it's, I guess, carefully written and it's what we expected. Now, the natural question is, why do we need dilation matrices for this to work? Yes, Brian?
Our old definition of the MRA was completely characterized by the phi, right?
Yes.
Once you need phi now, we need phi and...
Except that it wasn't, if you think of this generality, because in some sense it was also characterized by the matrix with all 2's down the diagonal and the lattice of integers.
Right, so now we need a lattice, a matrix, and phi.
Right.
Okay.
But you made a by implication, you made a very good point. The phi is not uniquely determined. Basically, if you're given an A lambda situation, then we're going to show that you can talk about an MRA is associated with A and lambda, but there might be lots of associated with that A and lambda. Okay, so the basic question is, at this level, is why do we need dilation matrices? It's convenient when we take, when we do this, of course, guess it's really related to is item number 4. And we want to talk about that property of an MRA. So basically I wrote up a calculation. It's a little bit long, but maybe I'll just sketch it because I want to give you the broader picture tonight, since it's sort of a Christmas gift or whatever holiday you celebrate. So given a lambda and take an a lambda MRA P and Vj. Let's suppose we have that setting. And in order for things to work, we usually need some sort of smoothness. Unless you have some ad hoc situation that you can just push through. But assume phi hat is 0 is not 0. So in particular, I can't talk about a function that's almost everywhere. I'm assuming, say, phi is also an L1. And phi hat is continuous in the neighborhood of 0. And just for the heck of it, define W to be equal to the union of the VJs. So in the spirit of just sketching this out, but I'm not omitting anything difficult, I promise you. Step number 1, we first show so we define that and want to prove W is equal to, I'm assuming, I guess I don't want to assume I have an MRA then, because I want to prove that W is equal to L2 of RD. So take, let's assume I have a phi and VJs, and that I want to verify that property of an MRA. So, sorry about that. So this is like an uncertainty principle situation with the chalk. This piece of chalk will last longer than all of us because it's so hard. On the other hand, this piece of chalk will probably break 4 times, but my hand will last through lectures. We'll switch to this piece of chalk. We'll first show that to show W is translation invariant, is lambda translation invariant. Okay. So we let F be in W. And we want to show that actually, I'm sorry for being sloppy here. To show W is RD translation variable. Let F belong to W and let T belong to RD to prove F, this function here, plus T is in W. We'll actually use this property of dilation right at this level here. So let epsilon bigger than 0 be given. There exists an integer L and function h in VL such that f minus h in L2 norm is less than epsilon over 2. Okay, that's just the property that I'm taking f in this closure of the union. And there exists a delta bigger than 0 such that for all r in Rd with Euclidean norm less than delta, f minus tau f in L2 norm is less than epsilon. Okay, and that's because of just properties of Lebesgue interval, right? And since all eigenvalues lambda satisfy lambda bigger than 1, then the eigenvalues, let me just write it a little sloppily because it'll take too much writing here, but you'll understand what I mean. Then the eigenvalues of A inverse are less than 1 in absolute value. And then, in the spirit of sketching a little bit, then you can show that therefore A inverse of ZD hold on a second. So I want to take, so I just want them small. So I'm going to take cut the lights, cut the sound. No, this is okay. Therefore, if I put a J here, these things here, this is dense in RD for that ball, I guess. We're making them all small, and we've made them all small enough so that they come in around the origin. Therefore, we can find the J in N union 0 and a lambda in the lattice. So I wrote this down for ZD, and I'm doing it for lattices, which is why one of the reasons. More hopefully than usual. Such that we may end up saying that ZD is equal to lambda, which is modular trivialities, but I thought I was going to be clever here. T is less than epsilon. there I am, I'm just looking in Euclidean space here. It's less than 12. Okay,
That first statement is for all J?
yes,
Okay. I mean, I just assume that.
yeah, it's for all J. Yeah, well, I can take J positive, but I just have to shrink them down. For all J. And so because of that, and because I started off with this T that I'm doing the translation with, I get this property here. Okay. So, I'm getting myself in deeper and deeper, although I haven't really sunk yet. Now, if I look at the translation by T of F minus the translation by A to the minus J of oh boy. So as I said, let's just take ZD. Okay. So the translation by J of M of that function H that I had, then if I add and subtract, write everything down, I'll certainly get myself in a mess. But the way I wrote it down earlier, it's okay. This comes out to be less than epsilon. Now, I really have used the fact that all the eigenvalues are bigger than 1, so that I could look at this dense subset. So I've used that. Okay? Doesn't seem very consequential, but I've used that plus. Yeah, Tom?
Surely you mean the union of all of those.
Oh, yeah, I do. Now, the way you said that then was, geez, getting sort of old, I'll be really nice to you. And that reminds me today, because I was talking with someone, and I was noting that I just read that one of my heroes just passed away, Andrew Gleason, solved the Japanese code and Hilbert's fifth problem and taught me real variables. That last thing was not high in his list of accomplishments, but so they were contemporaries of Mackey. Gleason and Mackey were contemporaries. And I used to refer to Mackey, and this is reverentially, as Wacky Mackey. And Mackey took over for Gleason one day teaching the real variables course. And Gleason gave an unbelievably intense course. And he went away for a day to give a talk, and Mackey came in and he said, well, Gleason told me to talk about, he listed some topics. 5 minutes later, after making slash marks over the blackboard, which was supposed to be his lecture, he said, boy, Gleason doesn't cover much material in this course, does he? So it's, but the person I was talking to today said, oh yes, he had Mackey for real variables, but more or less when he was 100 years old, which was, he died before that. Okay, but I do mean the union thing. Okay, so since H is in VL, we got H here now. H of X is equal to the sum of these constants. So depends on L, and B to the B's will be in ZD of B of A to the L X minus B. Okay? I'm just writing out the expansion of H in there. And then if L is bigger than J, and since A ZD is contained in ZD, we have that A L minus J of M is in ZD. So hence, meaningfully split up here, of H. When I do the calculation out, I get this is in VL, which is contained in W. And so now, combining this fact with the fact that W is enclosed in this fact, I get that this implies the tau TF is in W. Okay, I just messed that up so badly that that's step one of 3 steps for this proof, and I'm going to stop. Okay, because this is a pretty easy calculation, but basically I did use the fact here I needed the eigenvalues bigger than 1, and there's one other place in this verification where I need it, and it's related to getting the W is all of L2 market. Okay? I'm asking you to believe it. Okay. Now, the next step is we want to state this big theorem that allows us to get wavelets and wavelet orthogonal system. So let me do that.
This looks somewhat like that first paper in that book you edited with Fraser. Do you remember that?
In fact, let me talk about that, because it is. I mean, I'm taking. Historically, it's an amazing thing to me, because a lot of people get a lot of credit for doing this multidimensional business. But the first person that wrote this stuff down was Yves Meyer. What I'm about to talk about is Yves Meyer, and he did it in some lectures he gave in Torino in 1987. Now, many other people wrote research articles sort of replicating this. By the way, Strickhatz was not a research article. Strickhatz was just writing things out cleanly. And so there are two very, very good articles which expand on the Meyer article. One is by Wally Matic. And this is in a book that Charles Chewy edited in 1992 on wavelets. And the other article is the one that Brent just mentioned by Bob Strickhatz. And this is chapter 1 of the book that I edited with Fraser. 1994 on wavelets. Now it's done many other places, but Meyer was the first one to really write down multi-resolution analysis theory and prove the theorems. These Strickhatz especially, it's a very clean, beautiful exposition of this subject. And so after tonight, you might want to just have a couple of beers after this lecture. But then if you want to really see it written down beautifully, go check out Strickhatz's chapter. Let's see, anything else to say on that? Oh, I always acclaim correctly so the contributions of Bill Bashiz, because just around this time she did one of her first great pieces of work on wavelet theory. But she didn't do this. It was not unrelated. She didn't do this. What she did was she constructed smooth wavelet orthogonal bases. And that was a very difficult thing that she did, but not the same as this. Okay? But those two things were done in 1987. Okay, so we're in a situation of having a lambda, even though I didn't explain it so clearly. We need the eigenvalues in an absolute value positive, a bit bigger than 1, not only for this calculation, but for some other calculations. And we did prove, I did that correctly anyhow, that the determinant of A is in the set 2, 3, etc. And we're going to be looking at systems that look like this. Psi, L, M, gamma of X. It's going to be the determinant M over 2, and then psi L of A to the M X minus gamma, where L is going to go from 1, 2, etc. M is going to belong to Z, and gamma is going to belong to the lattice. And so this situation will be called a wavelet system. And the basic theorem that Mayer proved is the following. So theorem Mayer. So given A or an A lambda MRA with scaling function phi and scaffolding Vj. Then there exist L equals Q minus 1 constructible functions psi 1 up to psi Q minus 1 such that this set here, psi L M gamma, is where we run through L goes from 1 up to Q minus 1, M runs through all the integers, and gamma runs through the lattice, is an orthonormal basis for L2 around. So that's a basic theorem I want to talk about. Now, okay. Some more chalk. Yes, Tom.
Do we know what Q is?
It's the determinant of A, but it's there's a very interesting algebraic fact that comes up because we're actually going to count the number of cosets. I'll show you in a minute how that arises.
Mod out by lattice.
Yes. So, one of the ways of doing this is, I'm trying to decide what to skip and not skip here.
Just what you just said, if it was dyadic, the determinant of that matrix would be 2 to the d.
Correct.
but doesn't have to be in this. It could be something else here.
Yeah, and
Okay.
that's the amazing thing, because we're gonna see matrices up ahead that are gonna be full matrices, and that number of wavelets doesn't have to be a big number anymore. So, remember, I'm not sure if you remember, but I made the pitch that if you're gonna use dyadic wavelet theory, there's a flaw, and the flaw is you've got 2 to the d minus 1 wavelets. Now, if you're dealing with very large dimensional data, which one gets nowadays, then maybe that dyadic wavelet theory is not a good idea. But if you use the right matrix, now I made another pitch. I said, okay, then you go in the direction of wavelet sets, which you can do. But you can also go in the direction of other matrices where the number Q is going to come out to be 1, 2, something small, even though you're in D dimensions. So there's a tremendous, interesting flexibility, and all sorts of subjects get involved here. There's serious geometry, algebra, number theory, and of course analysis. So, so let me embellish this this statement of this theorem a little bit, and we've got the first sentence here, and we've got a function phi. So what? How can I do this? Rewriting the rule here. So I'm going to rewrite parts of it. So given this and this, let Q equal to the determinant of A, which we've been doing all along, and let AL, where L goes from 0 up to Q minus 1, be a sequence of functions defined on lambda and satisfying the following conditions. Namely, the sum where lambda is in the lattice of A L, let me use J and K, please. AJ of lambda, AK of A gamma plus lambda conjugate is going to be equal to Q times delta of JK, the Kronecker delta, delta of gamma 0, where gamma is in lambda, and the sum A0 of gamma, where gamma belongs to lambda, is going to be equal to Q. So so I've got given that, and now I'm going to block out this for the moment. Say, let Q be equal to that, and let these be 2 sequences to satisfy those conditions there. And in that case, then we define psi L of x to be equal to the sum AL of gamma phi of A x minus gamma for L equal 1 up to Q minus 1. Okay. Then these guys here, the psi, L's, M's, gamma, is an orthonormal basis for L2 of RD. So that gives a hint on how we construct these psi's. But where the heck do the A's come from? Well, what we're really going to do is, what one really does is, we have this MRA, so that means we have this increasing sequence of VJs. And so we look at V0, and then we look at V1. And so we write down V1 as W0 complete direct sum with V1 is complete direct sum of V0 and W0. Then what we know is, we know that properly normalized, that this is an orthonormal basis. So I've got a Q to the 1/2 here. There's an orthonormal basis for V1. And so then what we do is we write down Q elements of V1, Q minus 1 elements. So write down Q minus 1 elements, psi 1, psi Q minus 1 of V1, such that they are with such that they form an orthonormal basis for W0. Now, how would I go about doing that? The way I go about doing that is to just write down a generic element, psi 1, as a linear combination of these guys from V1. And I write down another element, psi 2, as an orthonormal, as a linear combination of these guys. But then I put conditions on them so that they're all orthogonal to each other, and they provide a basis for W0. And these are the conditions. And it turns out you can do it. So I spared a lot of chalk there, but that's the idea. Basically, let me just repeat that since, in case you lost track of my garbling here. But we have an MRA. We choose. We've got an A and a lambda. We choose a phi and a scaffold in Vj because we have an MRA. Now the phis form the translates on the lattice form an orthonormal basis for V0. These form an orthonormal basis for V1. I'm just going to pick out a bunch of elements. This is hindsight that I'm only taking Q minus 1 of them. But I'm going to take Q minus 1 of them, and I'm going to write each of these guys down, since they're in V1, as a finite linear combination of these guys. And then I'm going to play the math game of seeing what I need on those coefficients in order that those Q minus 1 elements form an orthonormal basis for W0. Okay. And these turn out to be the conditions. Now, there's work to be done to do that. It is not just pushing symbols around, but that's what goes on. Okay? I think I'm just asking myself how worthwhile it is to push through some of that arithmetic. Then well, let me do a little bit. But that's the idea. So, lemma if phi of x minus lambda in lambda is an orthonormal set, and if the A, L, lambda satisfy 1 and 2 here, then suppose we call this phi psi 0. Then these functions here, psi L of x minus lambda, where L goes from 1 up to, from 0 up to q minus 1, and lambda is in lambda, and psi L of x is this linear combination A, L, lambda in the lattice of phi of A, x minus lambda. Then that where is orthonormal. Okay? Now, that is truly a simple calculation. One just begins by writing down the formulas and using the orthonormality of this scheme. So I'm not cheating you or anything like that. So, proof. And then we want to know, which is one of the reasons we take this Q, we want to know, is it an orthonormal basis for V0? And to prove, so prove this is an orthonormal basis for V1. That is, these guys here, the set of all translates over lambda of the side L's. L equals 1 to Q minus 1, and lambda in lambda. Requires some work. Now we have all of the data with us here, because what we've done is we've written these things down here so that they satisfy that. And we got off a normality. We have to show it's a basis for all of V1. Well, here's where, when we originally developed multi-resolution analysis for the real line, I wrote down these conjugate mirror filters. And, say that again? I'm sorry. I have a translate by lambda, and then the function psi L. Oh, this should be up, you mean?
It should go from 0 to 2.
Oh, 0.
Or,
Thank you very much. Oh, you're excellent. What was that?
Or the V1 should be W.
Yeah, but no, but thank you. That's, I wanted to say it this way. Thanks. So, we want to prove this as a basis. Well, the way we prove it as a basis is we go back to the same trick that we used when we did the thing in one dimension for the dyadic case. We introduced these quadrature mirror filters, and you have that sort of complicated argument that we did. Remember I said it was the only hard part of the show. In fact, we can do this as we did for dyadic MRA on R in terms of conjugate mirror filters, where we consider the functions A, L, lambda in lambda, the functions for lambda equals ZD, say, of lambda in ZD e to the 2 minus 2 pi lambda, well, let's use that. Sorry, Bruce. N dot gamma in the torus. So there's work involved. You can see it's going to get complicated, but that's the broad outline of how one proceeds. Now it's 7:15. Maybe I'll take a 5-minute break now. And while I'm taking a break, people can bring their papers up.